The title I don't remember.
I also
Fractional
don't
modeling
remember.
in the gap.
Yes. Okay, thank you. This is the continuation of our previous lectures 2 days ago, and what we try to see in these lectures is how to use fractional derivatives to model, in this case, wave propagation in viscoelastic media, and then various possibilities for that. So we use fractional derivatives. We all learned what fractional derivatives are. Here I recall definitions of the Riemann-Liouville and left and right fractional derivative. There are also some other types. Let me just point out that maybe the main difference between fractional derivatives and integer order ones is that fractional derivatives are non-local operators. So you see, once you use them, you have, so if your variable is t, you take fractional derivative with respect to time variable, then since you have here integral from a to t, you in fact, let's say, take a complete history from some initial moment, a here, till your point t. So you take the whole interval, and in that case you can you have memory, and if you want to model some phenomena where it is important, then you can use fractional derivatives. And if the variable is x, so the spatial variable, then you model non-local effects, because you have your point t, and then you can, so depending whether you are in one or more dimensions, you can, the whole neighborhood of the point, which, and all points from that neighborhood, which is not arbitrarily small but fixed one, have their role in this definition, in the value of the fractional derivative. So that is the main difference between fractional derivatives and integer order ones. And so what we did is, I will just go to the first model we considered, let's say this one. So typically we have system of 3 equations. All 3 are different physical laws. So the first one is the equation of motion. Then we have constitutive equation, and then strain measure. And for this second one, constitutive equation, which keeps information about the media in which we consider wave propagation. So we play around this equation. So first and third we don't change. And the first case was this so-called fractional Zener model, where we generalized the classical Zener model by replacing first derivatives in the classical Zener model with fractional ones, as it is done here. And then we, so the first step is to provide, to derive the corresponding wave equation from this system. And as you remember, we do that by applying first the Laplace transform to the second equation, then insert epsilon, so the strain from the third one to the second one, and then everything to the first one, and we obtain the corresponding wave equation. Okay, we started with this Zener model. Later on, we generalized it to arbitrary linear combination of fractional derivatives, that is the so-called linear fractional model. And going a step further, so taking somehow into account all possible fractional derivatives of order between 0 and 1, we arrived to a distributed order model. So instead of Riemann-Liouville, we use distributed order derivative. And now we want to see whether it is possible to use fractional derivatives of complex order. As we said, it is possible to define such derivatives. In fact, the definition is more or less the same. And if yes, so if it is possible, why and how to deal with complex derivatives in such models. So let me go. Yes. Okay. So as I said, now we want to check whether we can use fractional derivatives of complex order. And as before, the thing which we have to take care about from the very beginning are those thermodynamical restrictions. So as I said previously, well, you can put in constitutive equation whatever you like, but the question is whether it makes sense. In the first place, physically. So, is it okay from the physical point of view, meaning that whether the second law of thermodynamics is violated or not? That is the thing which we have always to check. But one more thing, when we deal with the complex order fractional derivatives, one more thing which we have to care about is, so once you apply fractional derivative of complex order to real valued function, in general, we will obtain complex valued function. And that is something which we would like somehow to avoid. We would like to stay in the real domain, so to work with real valued functions. So the first problem which we had was to think how to choose, or is it possible to choose fractional derivatives of complex order in a way that once you applied it to real valued function, you obtain again as a result real valued function. And so, because the constitutive equation relates stress and strain, this was the question. And the first attempt, it was just, okay, let's put sigma is proportional to the fractional derivative of complex order of strain. The answer here is no, so in general that would be complex valued function, and as I said, since we want sigma to be real valued, we cannot take this type of equation, so it would not work. And then, okay, while calculating things, we realized what is the problem, what can be fixed. So, if we take a combination of two fractional derivatives of complex order, such that they are complex conjugated, so the same real part and just minus in front of the imaginary part, with the same coefficient in front of those. And we also remember that these coefficients are important. Then such equation is acceptable from mathematical point of view as a constitutive equation. So we can have a relation where sigma is proportional to this linear combination of fractional derivatives of strain of complex conjugated order. Okay, and then the next question is what, for such equation, what the thermodynamical restrictions would be. Meaning, so if we go again through that Bagley-Torvik procedure, and I will repeat it here. So the question was that, so the procedure tells you that you should apply the Fourier transform to your constitutive equation, define the complex modulus, and then examine the real and imaginary part of that complex modulus. And the condition is that both real and imaginary parts should be non-negative. And first we tried with so this type of equation, so just linear combination of two fractional derivatives of complex conjugated orders. And so we couldn't find values of our coefficients, so this b and this beta, such that the real and imaginary part of the corresponding complex modulus are non-negative. So it means that now from the physical point of view, from the side of, so the second law of thermodynamics tells us that this type of constitutive equation is not acceptable. Mathematically yes, physically no. And then the next attempt was to add additionally term. Now it is fractional derivative of strain of some real order, alpha. And in that case, yes, we were able to derive thermodynamical restrictions. And you can see those thermodynamical restrictions here. Here is the calculation, as I said, apply the Fourier transform, define complex modulus, and then determine all parameters such that real and imaginary part of that complex modulus are non-negative. And those thermodynamical restrictions in that case tells you that this alpha, so this real order, have to be the same as the real part of beta. So you should add fractional derivative of real order, and that order is exactly the real part of this beta. And then two additional inequalities. Similarly as in the previous cases, when just looking at them, one should say that they are not very, how to say, natural or not easy to verify. But it turned out every time, whenever we were solving any of those models, that these thermodynamical restrictions, just exactly in this form, appear in the calculation of the existence of the solution to our problem. So it means that so these physical requirements and also mathematical requirements coincide very nicely in those models. And so, as a conclusion, we have that if we want to consider constitutive relation between stress and strain using complex order derivatives, such relation should be in this form. So you should always have a combination, linear combination of two complex order fractional derivatives so that the orders are complex conjugated numbers, plus the real order fractional derivative, and that order is exactly the real part of this complex beta, complex number beta. But this was just studying what type of constitutive equations are acceptable, and we wanted, in fact, to study now the generalization of the Zener model. And Zener means that you have the same situation in the constitutive equation on the side of stress and strain. So meaning that this type of linear combination of fractional derivatives we will have now also on the side of stress as well as on the side of strain. And in that sense we arrive to the following problem. So as always we preserve first and third equation, we don't change them. And now we choose for this constitutive equation for the second one the so-called complex fractional Zener constitutive relation. So in addition we have this term 1 on both sides, meaning just stress or strain itself, and then additionally these fractional derivatives, as I said, of complex order plus this one of real order. And for this system we wanted to consider the problem with initial conditions. I realized some mistakes here. So we wanted to have no initial displacement, no initial velocity, and no initial stress and strain. So also sigma and epsilon at x0 are 0. And then two types of boundary conditions. So either a bounded domain, so let's say imagine rod of finite length, and then you have on one end prescribed displacement, and on the other end it is 0. Or if you have let's say rod which is with one end and the other end is free, so unlimited. On the other side, then when you let x tends to infinity, you have that displacement is 0. So these two different types of boundary conditions, those are two different problems. And as always, we want this system to write in the form of the wave equation. In this case, it will look like, I can say as before, with the only difference in this convolution operator L. So the form is always the form of the wave equation, and now L is calculated when Laplace transform is applied to this constitutive equation. and then sigma is expressed in the term of epsilon, and with the inverse Laplace transform, so the operator L is the inverse Laplace transform of this quotient here. And all these terms here appear as a Laplace transform when applied to fractional derivatives of stress and strain. So the order of alpha is between 0 and 1. Beta is positive because we want to really to have a complex situation. So if beta is 0, then that is real order model, so what we studied before. Also, well, this is not a restriction, it is positive because we have complex conjugated orders, so that's okay. And for coefficients that appear in this constitutive equation, so for all these A's and B's, we want to be non-negative, A2 greater than A1. So this coefficient which is in front of the fractional derivative of real order, that was again from the previous case, from the real order case, and then thermodynamical restrictions. Okay, we had to derive them for this Zener model, similarly as in the previous case when we studied all possible constitutive equations, and that is given on the next slide. So those thermodynamical restrictions are given by these three relations. So the first equation, and you see here that coefficients A1, A2, B1, B2 are related by this equation, which means later on when we will be studying numerical examples, we just arbitrarily choose three coefficients and the fourth one is determined by this equation. And then these two inequalities, as I mentioned, although somehow not very nice at the moment and doesn't look that's to appear naturally for the problem, exactly those equations should be satisfied when we want to prove existence of the solution to our problem. And the strategy for solving this complex fractional Zener wave equation is, of course, similar as before. We will apply the Laplace transform to our equation. We will obtain equation of this type. Now it is ordinary differential equation with respect to x. This m squared, which appears here, is of this form. And, of course, we also calculate Laplace transform of our boundary conditions. And then we immediately can formally solve this equation and obtain the Laplace transform of our solution u. And then, again, as before, the question would be how to go back. So, to check whether we can apply the inverse Laplace transform, and if yes, can we explicitly calculate that inverse Laplace transform and obtain our solution in analytical form. And so our solution, depending whether, as I mentioned, two sets of boundary conditions, so bounded or unbounded domain, half-bounded domain, it will influence the form of our solution. So now I see again some mistakes. Here it should be tilde. Okay, it is Laplace transform, not Fourier. And then in the case when we have bounded domain, our solution or the Laplace transform of our solution is given by this expression, or in the case of half-bounded domain, it is given by this expression. So the question is to examine this function m, to learn everything we can about it, so to see whether we can invert it in Laplace domain and how to do that. And the results are the following. So maybe I can do something. So a lot of calculation, one should be very careful because you easily make some mistakes and go in bad direction. But okay, once you do that slowly and carefully, you obtain, so that's m squared is in fact 1 over our complex modulus. And then the real and imaginary part are given by these expressions, where again we use some short notation for this B, C, D, and you can see how they look like in these formulas. And they also involve functions f and g, which depend on tau and phi, which are in fact when you write down how your arbitrary complex point look like, so arguments. This phi is argument of your complex point. And then, okay, the first result is that we have maximal and minimal values of those functions f and g at the points written here. Then, if we assume that those expressions c and b, the ones we saw on the previous slide, are non-negative, then we have that the real part of m squared is non-negative, which is one of the things we wanted to have. Also, there exists some point in which, for which imaginary part is negative, starting with p greater than that point p 0. And also, we prove that M has no singular points with positive real part, and for that, this time we used the contour of this form here. So, after all these calculations, checking conditions, we were in fact able to prove that assuming all those restrictions on our parameters, from the beginning, we can calculate the inverse Laplace transform of M, and our initial problem, so our wave equation with initial and boundary conditions, as we gave in the beginning, has a solution which is convolution of the boundary condition with a kernel, K, which is given by this formula here, when L is, so on the bounded domain or on unbounded domain, the formula or the expression for the kernel is given by this formula. And also, still, this is, let's say, proof that we have, that our problem is solvable, that we have a solution. But from this result, we still don't have explicit form of the solution, and that was possible to calculate only in the case of unbounded domain. So in that case, we can have a more explicit form of our kernel K, given by this formula here, and again, it is obtained by integration. Now the contour which we used is given here, and so this is the K which we can obtain. And let me give you a numerical example. So here we choose, as I said, remember we had 4 constants in our Constitutive equation, and the relation from the thermodynamical restrictions that relates these 4 constants. So 3 we choose just arbitrarily, that is A1, A2, and B1, and then we calculate what B2 will be. We consider here the case when L is infinity, so how bounded domain, because in that case we have this previous formula to calculate the real solution, and we can then use numerics to do that. And for boundary condition, so remember it was one end of the rod. On one end we prescribed displacement, and we choose that to be direct delta. In that case, we have that the solution to our problem looks like this. And then here we choose 2 sets of values for alpha and beta. Remember, alpha so the orders of fractional derivatives that appear in our constitutive equations were alpha, and we choose to be 0.5 or 0.7, and then alpha plus E beta and alpha minus I beta, and for beta, so for that imaginary part, we choose 0.1. And if you just look at these pictures, so you see here your solution U, which propagates with time for these different two sets of values of fractional derivatives. So the initial displacement which propagates is this Dirac delta, and you see how at the same, this is the same time instance in both cases, how it looks like after some time t. But what is interesting here, maybe it is not very well visible, but here at the very beginning, also here, we have kind of small oscillations, a pulse behavior of our solution. And that is something which we can connect to this complex order derivatives, or this imaginary part of order of fractional derivative which we have in our model. Because as you remember, in all previous cases and in all previous numerical examples, we didn't have such thing. And in fact, in the first moment we were like not sure whether it is okay or not, it has physical meaning or not. But then we looked at some experimental results in which, in some rheological models, when experimentally they measured how initial disturbance propagates with time, and then they realized some of those oscillations in the beginning, but since it was not theoretically approved, or there were no evidence from the analytical point of view that something like that can happen, they concluded that it is a consequence of the measurement instruments which are not precise, or maybe, and then such pulse behavior appears in the beginning. But with this model and with complex order derivatives, we can now also theoretically describe this situation which happens, as I said, which is also experimentally verified. Later on, we also studied this model, but on completely unbounded domain. Again, the techniques and analysis which we did, it differs from this situation, because it always depends whether you have finite domain, infinite, or half-infinite domain. And we also obtained results in that case. I didn't prepare that for today. Here I have a list of references in which all of these results were published, and most of the work was done with my colleagues from University of Novi Sad. So in the first place, I will mention Professor academician Teodora Tanackovic and Stevan Pilipovic, and Professor Pilipovic you met here in this school last week. So the cooperation started with them, and later on we continued. So Dusan Zorica, Ljubica Opanica, who I believe you know all, and who it was there, Marko Janev. So it was really interesting to work all together, because Professor Tanackovic and Marko Janev and Dusan Zorica, they are physicists, and they come more from the application. So they were the guys who provided all those models, who then we calculated things, and at the end, whenever we did some numerical examples, they were there to tell us, oh, that is stupid, not work, not good, let's check things, or it is, yes, it is physically reasonable, we can accept that. So that is how we
somehow have good relation between theoretical side of the story and applicative side. And also I mentioned several papers during this presentation, so I'm sure you also learned from Professor Kyriakova and maybe some other speakers during this summer school that there are nowadays many people working in the area of fractional calculus, applying it to various problems. And well, I extracted here, in fact, only those, let's say, monography books from which we learned the theory, like the most famous one is Sam ko kilbas Mariče, or Kilbas Trinastrava Truiljo, Miller Ross, and so on. So if you're interested in the theory, you should start from reading these books. Yes, there is also, in fact, it is in 2 volumes, the book by Atanacković, Pilipović, Stanković, and Zorica, where they collected, well, different problems which we were solving in using fractional derivatives, and also the problems I presented here. Okay, and for the end, I also wanted to present well, another problem in which we used also fractional derivatives, a bit different from the previous ones. This is a problem of Euler-Bernoulli beam, which is which laid on the viscoelastic foundation, and so it is described with this system, these 2 equations. So in the first one, you see this operator Q, differential operator, and its explicit form is given by this expression here. And then this viscoelastic foundation on which our rod is positioned is given by you can recognize here, fractional Zener model. We used it several times before. And we have initial and boundary. It is a finite rod of length 1. You see some initial and boundary conditions. And what is, such type of models were already studied in the literature. What was new here? First, use of these fractional derivatives in the Constitutive equation. So it is a fractional model. And then the question was, if we put here for these coefficients C and B, let's say we have some singularities on these 2 places. So how to properly solve such problem? And this is work done with Ljubit Oparica and Günther Hermann. The first thing one can show is that this system is equivalent to this equation, plus initial and boundary conditions, and the equation is obtained as before by applying Laplace transform to the Constitutive equation, and then insert g from it into the first equation and obtain the one you see. Sorry. And so motivation is is this equation of the transversal motion. I'm sorry, that happens sometimes. You have here explanation of all functions that appear in this equation. So A is the bending stiffness. You see it is given in the form, here we have Heaviside function. which means that we have a rod which has, how to say, two different cross sections. So in one moment the cross section changes. So let's say from thin to thicker part. This R is line density. Again, we suppose that it is different on these different two parts of the rod. P is actual force, and you see here it is given in terms of direct delta distribution, and that is what makes problem here with the classical theory. So the classical theory cannot deal with the coefficients given in this form. And G is a force term coming from the foundation, and H is prescribed external load. And as I said, the beam, so this is the equation which describes the transversal motion of the beam, and that beam laid on the fractional, on the viscoelastic foundation, which is described by the fractional Zener model and which influence the behavior of this beam. So these two equations, when coupled and after introducing some change of variables, provides us with the problem which I presented you on the previous slides, the problem which we are going to solve. And so what was the idea here? So since we have in these coefficient functions distributions, we considered the most appropriate setting for treating that problem, the algebras of generalized functions in the sense of Colombeau. So I don't know how familiar you are with the notions of Colombeau generalized functions, but I'm sure that most of you are familiar with the notion of the very weak solutions concept, which is kind of a similar notion. And but okay, here we used Colombeau generalized functions, which means that so if you, what is the problem in the spaces of distribution? You cannot multiply distributions. That is not very well defined, and then you embed your space of distribution into, well, space of, let's say, smooth functions with some conditions on growth of that functions. You obtain nets, and then you can do regular operations on those nets. And it is always the question whether you can go back once you obtain a generalized solution. Do you have, it is called distributional shadows, and how do you have a function or a distribution that you can associate with a solution in the sense of generalized functions, so to that net you obtained. And there are different possibilities for so typically you define those moderate families and null families, and then you make a quotient space, and that moderateness and negligibility you can do in different kind of spaces of smooth functions. Here we suppose that U epsilon, so the nets, the elements of those nets are in H infinity, and then moderateness means that each derivative you can bound it by some inverse power of epsilon, and then for negligibility or for null families you have that, so such a net is a null element if each growth of your functions are bounded by any power of epsilon. And you make a quotient, and that is the space of generalized functions in the sense of Colombeau. So our idea was to solve the problem in this space. We considered it as the most appropriate space to treat the problem which I showed you at the beginning, because in those coefficients we had distributions, and we need to multiply, to work with them. So to embed the problem in those spaces of Colombeau generalized functions, there the theory is already well developed to solve problems in those spaces and to find generalized solutions. And that is exactly what we did. But, well, step by step, first we considered an abstract problem. So it takes the form, you see, in fact, you couple, let's say, your initial equation with a function v from space V, and here you choose some, for V and H, some separable Hilbert spaces. V is densely embedded into H, and make a Gelfand triple. And in addition, there is assumption A, which we have to assume. It means that we describe this bilinear form A. It will be given as a sum of A0 and A1, and they should satisfy these 5 conditions. So meaning that A0 is continuously differentiable with respect to t, symmetric with respect to u and v. Then A1 is, let's say, A0, sorry, is bounded from below in this sense. A1 is continuous, and also we have this upper bound for A1. So in this abstract problem, with this assumption A and assumption L on this operator L, and for L we assume that it maps L2 space to L2 and satisfies this inequality here. So assuming A and L for this abstract problem, it is possible to prove the existence of a solution, and so that solution in addition satisfies the regularity condition. So U prime is an element of EV, the second derivative is in L2, and moreover our solution is continuous, and the first derivative is also continuous. U is with values in V and U prime with values in H. Also for this abstract setting, so this abstract setting is of course will be used later on for our concrete problem. We were able also to prove energy estimates. They are necessary for later on for proving uniqueness of the solution. So we proved these energy estimates for our solution U, and then also uniqueness of the solution. So those are results for the abstract problem. Then, so the aim was to go further to our situation with so into the algebras of generalized functions. And we also needed the analysis of operator L, that is the operator which appeared in all our equations we considered. So it comes from the Constitutive equation once you apply Laplace transform and then do the inverse Laplace transform. So some properties of L were derived in these two results. Okay, and then first we do that for weak solutions. So we now choose concrete spaces for H, V, and V prime, so the dual. Those would be L2 space and Sobolev space H20, and also for EV and EH. And we check that conditions for that operator, that bilinear form A and for L are satisfied. Those we previously had for the abstract setting. So if you take into consideration this situation here, so with these spaces, then assuming AV and LV, also for initial and boundary conditions, assumptions that they belong to certain spaces, then we were able to prove existence and uniqueness of a solution in L2 with additional properties that the derivative is also in L2 and the second derivative again, but with different codomains. And this solution, of course, satisfied the initial value problem. But still, with these weak solutions, we didn't cover situation when we have in coefficients of the system, for example, Dirac delta, as I mentioned in the beginning. So the next step was set up for the Colombeau generalized solutions, which means that now we will make a convolution with nullifier of the whole problem will be in fact embedded in those Colombeau generalized spaces. That means that we make a convolution of each function with a modifier, and then corresponding assumptions on our form A and our operator, convolution operator L, are given by these two things here. Okay, this is a resilient result. And so now, assuming these assumptions AG and LG, so assumptions on A and L in this generalized setting, we were able to prove existence and uniqueness of a Colombeau generalized solution, as I said, using techniques from this theory of Colombeau generalized functions. But let me just say, as the last remark, unfortunately, we were not able to prove existence of the distributional shadow. So we know that we have a Colombeau generalized solution, but we don't know whether we have distributional shadow or, let's say, a generalized solution in the sense of distributions. And that is all I plan to say, so thank you very much.
Thank you. Any question or comment?
You mentioned you were talking about fractional viscoelastic models, and when you use the complex order, like alpha plus I beta, is there any physical interpretation of the imaginary part?
As I said, not really, but what we, I mentioned that in this example, what we could explain by the use of complex order derivatives is that the behavior of the solution, which by the use of real order fractional derivatives cannot be that
oscillation.
Yes, those oscillations.
And
yes.
Is that oscillation actually seen in kind of experimental data?
Yes,
Okay.
yes, exactly.
All right, thank you.
And as I mentioned, such oscillations could not be explained theoretically, so it was like thought that it is maybe error of some instruments, maybe that comes from not precise instruments or such things. But now, using these complex order derivatives, we can explain that. Although, yeah, it is not natural, so what would be a physical interpretation?
But you need the complex order to make sense of what happens physically. Okay.
Yes.
That answers my question, thank you.
So in the numerical like graphs, you had different alphas. Yeah? In one there was a disturbance, in the other there was none.
Yes, but small one.
Okay.
And in that case, let me go back. maybe not because that was a... Yes, also here there are, but
There is
maybe it's more. And how we can explain that, since this real part is here more dominant, and the imaginary part is small, the model behaves more like in the real case, so that you have, this is closer to one, like you have just a real order fractional derivative. But still there are small oscillations here, but smaller than in this case. So that is the only explanation we could provide.
Okay, thanks.
I also have one.
Mhm.
So when we're working with variable solutions and define the models of a net,
Mhm.
The condition is not for the derivative of any order. In your case, I think it was for any order, for any alpha, right? But how can you check this condition?
How
How can you check this, the derivative of any order?
can I?
How can you check this condition on the
Check?
models? Yes. I mean,
Without
I don't know,
any
maybe
problems.
it's a bit naive the question.
Yes, no, but you check that. You mean this condition of
Yeah.
moderateness?
Mm.
Yes. But, you mean when for the solution?
But I guess this is also for the for
But you check without any problems. You have here, let's say, smooth functions. You know that you have all derivatives of that function, and then you just verify that it is fulfilled. It is not a problem to verify it. Well, it is calculation, some calculation, but you do that. You always do that whenever you work with Colombeau generalized functions. Because you obtain, like, in your problem, you put, let's say, epsilon everywhere, which means that you make a convolution. And then you have a net of system, how to say, and as a solution you obtain a net of functions which solve your problem. And then you know that it is, you started from the C infinity case, you obtain C infinity function, it has derivative, and then you calculate it and check that this condition is satisfied, that you can bound each derivative by the inverse power of epsilon.
so you don't
Just
require
direct calculation.
so you don't require this condition for parameters in the Cauchy problem.
I require this condition whenever I go into the space of Colombeau generalized functions. So for each net, so whenever, but it is also checked when you make a convolution with a modifier, you take element of d prime, whatever, you make a convolution with a modifier, you obtain net of moderate functions that satisfy this inequality, as it is written here. So it is, how to say it is already theoretically confirmed that d prime can be embedded into the space of Colombeau generalized functions. So you start from any distribution, you make a convolution, you obtain a net of moderate functions. And then you work with system where you have those moderate functions, find solution, then for solution you check that it is also moderate or negligible, or it depends, by checking simply this inequality for arbitrary derivative. You really do explicit calculation.
Okay. Anything on it?
And for the last theorem, when you have solution with the Colombeau algebra, I guess the question whether it has distributional shadow is the most interesting.
Yes, of course, and the most difficult. And we tried, but we couldn't, in that moment we couldn't find out, as I said. That means that, so we couldn't prove either that there is or there is not, but it is always the most difficult part in the theory. So we know there is a generalized solution in the sense of Colombeau, but the distributional shadow.
Someone else? Okay, then thank you again.